Okay, so one of the first things that we're going to talk about in this unit um, is pulses on a coiled spring. So usually I do this as a overall lab demonstration, but since you guys aren't in the classroom, what we're going to do is just show you a couple of video clips of the parts that would be really important for you to know in order to get a good understanding of waves. So for starters, there's a couple key terms that you need to know. The first key term is medium. So a medium is anything through which sound travels or which a wave would travel. Some examples would be air, water, gases, other types of liquids, solids, etc. Propagate. Propagate means to travel through. And a pulse. A pulse is a packet of energy. So we're going to talk about two types of pulses, or essentially waves, today. So what I want you to do while you watch the short video clip is to sketch the pulse. After you've sketched it, describe the movement of the individual coil of the spring relative to the motion of the pulse itself. Okay, so here's the first wave. Watch how the hand is moving relative to the pulse. The pulse is moving to the right, and the hand is moving up and down. And here is going to be another viewpoint of the same scenario. This time, the pulse is going to be moving toward us, and then back toward the hand, and the hand itself is moving left and right. So those two directions are perpendicular to one another. Okay, so let's recap the first wave type. So this is called a transverse wave. So as seen in the video, the hand is moving perpendicular to the wave motion itself. So in this visual, you can see that the coils, individual coil, is moving up and down in the same direction the hand is moving. And the wave, or the pulse, or even we could call it a packet of energy, is moving right. So these two motions are perpendicular to one another. We call this a transverse wave. Some examples of transverse waves are going to be light waves, water waves, etc. Okay, so the next type of wave is going to be shown right here. And you can see with this slinky that the wave pulse itself is being sent down the slinky to the right. So the individual coils are moving to the right, and also the wave itself was moving to the right and back to the left again. So those two motions are parallel to one another. We call this type of wave a longitudinal wave. Okay, so let's recap that second type of wave. That wave that we just went over was a longitudinal wave, and we could see the source of the wave, the hand, was moving to the right and back to the left, and the individual coils themselves were moving to the right, to the left, and the wave itself, or the pulse, the energy, was being transported to the right and back. So these two motions relative to each other are parallel. We call this type of wave a longitudinal wave. An example of a longitudinal wave would be sound, or even sonar. Okay, the next thing we're going to look at is called interference. Interference refers to the behavior of pulses as they encounter one another while coming from opposite directions. What I want you to look for is whether or not the two pulses are bouncing off of each other or whether they go through one another in these next few video clips. We are eventually going to draw a before, during, and after picture of what's happening when these two pulses interact. But let's think about, for right now, whether they bounce off or go through each other and how we know. Okay, in this first clip, we can see a coiled spring in front of us, and two students are sitting on the floor, and they're about to show us a pulse being sent down on this side and a pulse being sent down on this side. Okay, so we can see that there's a pulse being sent down here, and in the middle, something happens, and then the pulses do something else after they interact. So let's rewatch that one more time. So make sure you pay attention to the size of the pulse being sent down on the left and the size of the pulse being sent down on the right. to help you decide on how they're interacting in the middle, whether they're bouncing off each other or going through each other. So at first we can see the pulse on the right side is smaller than the pulse on the left. But then after they go through each other, the pulse on the left is now smaller than the pulse on the right. So what we should be seeing is that the original pulse that was sent down from the right side has now gone through the other pulse and is on the left side. Same thing with the other pulse. The one that was sent down originally this way on the left side has now gone through to the right side. Okay, so for first we can say that they are going through each other. The next thing we want to look at is the type of interference this is. So if we rewind the video just a little bit and you watch what's happening when they interact. So you can see when they interact that the two pulses combine together to form a really large pulse. So originally the one on the left side was about 1 tape length high, and the one on the right side was 2 tape lengths high, and when they combine, they're 3 tape lengths high. We call this constructive interference. And we can remember this because when we think of the word construct, it means to build. So it builds a bigger wave. Let's go ahead and draw a before, during, and after picture of what's happening here. Okay, so for this first type of interference, we had, for our before, we had one wave pulse being sent down on this side. And then we had another one, and I believe there are 2 different sizes, so it doesn't matter which one's which to start with. We'll just say the bigger one was on the right. And it's being sent to the left, and the left one's being sent to the right. And during, we noticed that they combined together. So however high this one was, we could say that this one was a height of x, and this one was a height of 2x. So in the middle, when they combine, they should be a height of 3x. And this type of interference is called constructive interference. Remember, construct means to build. And after they have interfered with one another, we noticed that this larger one on the right side has traveled through the smaller one. It ends up on the left side. It ends up moving the same direction it was originally moving, toward the left, and the one that was on the left continues moving to the right through the other one. And they keep their original size that they had to begin with, assuming that all energy is being conserved. So this type of interference is called constructive interference. Okay, let's go ahead and look at the next type of interference. Okay, so here is the next type of interference. So in this kind, we can see that the 2 pulses are being sent down on opposite sides of one another. So one is sent below this horizontal middle line, which we could call the line of equilibrium, and one is being sent above the line of equilibrium. And when they interact, they aren't building up any longer. They're actually almost completely wiping each other out here in the center. So what we call that kind of interference is destructive interference. Let's watch that one more time. So they start out on opposite sides, and when they interact in the middle, they destruct one another, but then they continue on through one another. So originally, the one that was sent down from the right side was on the top, as seen, and then after they interact, it continues on the top through the other one. So they continue down the side that they were originally sent on. Okay, let's draw pictures for this. Okay, so let's go ahead and draw a picture of what we just saw. So we saw that the wave on the left was underneath the line of equilibrium, and the wave on the right was above the line of equilibrium, and they were about the same size. And we know that they were about the same size because in the middle, when they interacted right here in the middle for the during, they completely wiped each other out for that brief second, which we call destructive interference. And when you think of destructive, you should think of tearing things down. And then after they've interacted, and I don't know why I keep writing interferences. Could get rid of that. After they have interacted, this one on the right has gone through this one, so it continues above the line of equilibrium. And the one that was originally from the left side continues through under the line of equilibrium. And they remain the same height, however tall they were, after they interact, assuming all energy is being conserved. So the next thing that we're going to look at is called reflection. So reflection of a pulse occurs when it reaches the end of the spring, and then the energy is returned to the point from which it was generated. There's two types of reflection, both fixed end reflection and free end reflection. I want you to be able to draw a before picture and an after picture of before it reflects and after it reflects for both of these scenarios. Okay, so here we're going to watch the first type of reflection. So we can see the end on the left side is going to be where it's reflected off of. The pulse was sent down on the top above the line of equilibrium, and it's being reflected back below the line of equilibrium. We call this kind of reflection fixed end reflection. So let's watch that one more time. The wave pulse is being sent down above the line of equilibrium. It interacts with the fixed end, and it returns on the opposite side of the line of equilibrium. Let's watch another video of this. So here's two kids with a slinky in a hallway, and they're going to perform the fixed end reflection as well. So the pulse was sent down on this side, and then when it reflects off the fixed end over here, it comes back on the opposite side. Okay, so fixed end reflection, we can see that the pulse is being sent down on one side of the line of equilibrium, and it returns on the opposite side. Okay, here's one last video that shows the other type of reflection, which is going to be called free end reflection. So on the top, once again, this is fixed end, and free end, you can see, is the opposite. We can see the wave pulse is sent down on the top, and it also returns on the top. Sometimes this is hard to see in real life situations, so we could use a PhET simulation to also show this. So let's send a pulse, and let's make it a free end, so a loose end. And here's our pulse being sent down on the top, and it returns on the top. And then again, for a fixed end, it's sent down on the top, and it should return on the opposite side. Okay, so let's go ahead and draw these two scenarios as well. Okay, so the first type of reflection that we went over just now was fixed end reflection, where the end that the pulse is traveling toward is not allowed to move free, so we're just going to draw it as a solid circle. The pulse was sent down, let's say, above the line of equilibrium to the right. When it interacts with this fixed end, it's going to return on the opposite side of equilibrium, so on the left, going this way. And for the other case, it was the free end reflection. So let's say, once again, that the pulse was sent down on the top, and we're going to draw it as an open circle at the end for a free end. It would also came back on the top, above the line of equilibrium. So the next thing that we're going to want to look at is what affects the speed of a wave pulse. The spring is the medium through which energy is being propagated in our scenarios, typically. A larger amplitude pulse represents an increased amount of energy. Since we're not doing this live in the classroom, we can't use a spring in this video. So instead I'm going to use the PhET simulation to help you test out what exactly affects the speed of a wave pulse. Some options might be the following. Whether or not the speed is dependent on the amplitude of the pulse, so the amplitude's the size, or if the tension of the spring affects the speed of the pulse. So let's go ahead and investigate both of those. Okay, so we want to investigate what exactly affects the speed, and a couple things that we're trying to see is if the amplitude or if the tension affects the speed of this pulse. So our pulse is going to travel from this side all the way to this side. So it's going to travel the same distance in both cases. So we're going to keep that constant. And we know to figure out speed that it's dependent on two things, the distance and the time. But since we're keeping the distance the same for both of them, all we care about is the time. If one has a faster time than the other, that means it traveled at a different speed than the other pulse. So let's start with a pulse with an amplitude size of 0.7 centimeters. So let's go ahead and let me see if I can get these going at the same time. So as soon as I add a pulse, it starts my time, and then let's stop it. So as soon as the pulse got to the other side, I clicked the stop button. So it took 4.29 seconds for an amplitude of 0.7 centimeters to get there. So let's go ahead and restart. And let's change it. Let's increase our amplitude and see if it takes a different amount of time. So here we go. And then I'll stop it as soon as it gets back to the other side. And you can see that it's about the same time, 4 seconds. So it took, since it took the same amount of time to cover the same distance, that means it must have been traveling at the same speed. So let's go ahead and mess with the tension this time. Let's just use this last run as our baseline run. So it took about 4 seconds for a tension that is in the medium range. Well, let's increase the tension of this wave. Increase it, reset our time, and we'll time one pulse again. And clearly we can see without even having to, oops, I didn't stop it fast enough. Obviously it went way too fast for me to even stop, so let's watch it again and time it. And I'm gonna make sure I stop it right when it gets to the other side, and it took 2.68 seconds for that pulse to get back, so a lot faster. So we can see that speed is affected by the tension of the string. So the more taut the string or spring is, the faster the wave will travel through it. So the last concept that we're going to talk about for our introduction is called refraction. So refraction occurs when we have a junction between two different kinds of medium. So one spring, in this case, is going to be attached to a different kind of spring. Each of the springs have different densities. So let's check out a video for this. Okay, so in this video clip, we can see that we have two different kinds of springs attached to one another. We have a typical slinky type spring, then we have a tightly coiled bound spring. So this spring up here on the top is less dense than this spring on the bottom, which is more dense. So let's watch what happens when we send a wave pulse from the less dense medium to the more dense medium. Okay, let's watch that again in slow-mo. We can see that part of the wave goes back through the less dense medium and part of it goes through the more dense medium. So let's look at that again. It's sent down on the top and then it reflects on the bottom, so it kind of acts like a fixed end reflection at this point for the part of the wave that was reflected backwards, but also part of the wave was transmitted through to the other medium and it remained on top, which means it acted like a free end reflection type point. Let's watch that one part one more time and look at the speed of the wave while you watch this time. So it goes fast through the low dense medium, and then it continues on through the high dense medium at a slow speed. So speed is something that changes when a pulse or a wave moves from one medium to another. Something else you might want to note is that upon the boundary point, part of the wave is reflected backwards through the original medium, and part of the wave is transmitted through the next medium. And it continues with a fast speed through low dense mediums, and it continues with a slower speed through high dense mediums, as you've seen right here.